So this is kind of where the rubber meets the road, so to speak, of what I'm trying to do with this whole channel. You know, I want to try and take the engineering side of the equation, I want to take the furniture and the carpentry side of the equation, and I want to kind of join them together so that you have an appreciation of what it is that I'm looking at when I look at these things. And the first thing that I'm going to look at and talk about is a table. And the reason why I'm going to use a table to start with as my first kind of foray into this sort of subject is because it's a simple item, really, when it comes down to it. You know, at a very basic level, 4 legs, a flat top, you know, what really is it doing? But by understanding what it is doing and specifically what we need it to do, we can appreciate kind of the structural, the nuance to it. That's really what I'm trying to get at. And in order to understand what we're talking about here, because I'm going to talk about some engineering subjects that you might not be familiar with. So to start with, when we're talking about furniture and talking about any sort of piece of structure, what we're talking about is a design envelope. So we're not looking to design something for one particular scenario. We're looking to design it for a couple of different scenarios, and then by that particular item being able to achieve a particular strength in each of those scenarios, then we would say that it has a certain level of robustness. And that's really how we define robustness. Robustness is defined as, you know, can it survive in a real environment? Can it survive these individual tests these individual scenarios that we're going to impose on it? And if it can meet those tests, then we would define it as robust. So, what makes a robust table? That's what we're getting at here. So if we're talking about a table, or once again, we're talking about any structural item really, but specifically for this episode, we're talking about a table, then we want to define what that structure, that loading envelope, that scenario envelope could be. So a maximum and a minimum, and where does that maximum and minimum, what's the worst case scenario that a table could possibly be subjected to? And when we're talking about buildings specifically, we'll move away from just carpentry for a moment. When we're talking about buildings, we have a whole set of documents and standards which define the series of tests that a building or a structure needs to be able to withstand. So these are the sorts of conversations which we don't have, because the whole thing is set out very, very clearly, you know, very, very well defined in a set of documents which everyone adheres to the same documents. So although this is a really relevant conversation for tables, for buildings it's already defined for us. So if we go into furniture, the sort of tests that I think, because that's really what we're talking about here, there's no technical document which is going to tell us how to design a table. That just doesn't exist. We have to be able to make a robust table by what we conceive to be robust, and so we have to define that envelope ourselves. So how do I define that envelope? Let's just start right there. So if we imagine a table, crude sketched, it gets the job done, I think. The sort of scenarios I think about, the sort of envelope that I think about, are this suite of tests that I want this table to be able to perform against, would be as follows. So, I mean, to start with, I want to be able to sit on it. You know, it needs to be able to take my load, my weight, and, you know, potentially if we can get 2 people on here, then we might need it to take 2 people. You know, that's the sort of thing, you know, if a table can't really withstand the force of someone sitting on it, then in my mind it's not robust. That's the primary thing it should do. You know, I tend to look at glass coffee tables and other fancy bits of furniture. I think, you know, if I can't sit on that, if I have to worry about putting something down on it and that's going to break it, then that's not robust in my world. So that's the first thing it needs to be able to do. It needs to be able to take some vertical load. The second thing it needs to do is it needs to be able to take some horizontal load. So we've got to imagine that we're going to be pushing this thing around, we're going to be shifting it about, and that's going to cause friction on the feet from the floor. You know, if we're pushing the table in this direction, say, that's going to cause friction on the feet on the floor, and it's going to these are going to start bending. And if for example that we only had, you know, a single screw in here, then technically this could rotate around that screw, and as we pushed it, you know, technically it might be able to support the vertical load with 1 screw in there, but once we start pushing it about, it might start wobbling, and we don't want that wobble. We want this to be solid and secure. So I mean, to be honest, those are the two main tests. I would, we've got this vertical load, we've got this horizontal load, and then we would apply that same kind of horizontal load in this direction as well. So we want to be able to shift it in this way, we want to be able to shift it in this way, and we want it to stay secure. That's the idea. In my mind, the envelope of the things that we need it to be able to achieve. And in order to get that in order to get the table to be able to achieve that, we need these two bolts. I mean, in this particular configuration, we need these two bolts. When we have one bolt, it acts as a pin and the whole thing rotates around it. So in order to get these two bolts, the two bolts they provide a couple. They prevent any moment from being transferred. I talked about this in my structured design video. So in order to get those two bolts in there, or two big screws, we need a decent depth of piece of wood to be able to get them in there. That's really what we're talking about, and that kind of defines, in order to get these two in there, that kind of defines what this piece of wood, this cross member, is going to be. Because in order for this to have this kind of this force on it, it needs to transfer that force into something else. If that was just into the top of here, then it would just bend the flat table. So we need something solid and secure to be able to hold it, and that's what this kind of cross beam is doing. And in order to get that, we need these two bolts so that we can get this moment connection between the two. Now, the configuration of this table is what I would call the cantilever leg design, and it's because these legs are acting as cantilevers. They might be supported on the floor vertically, but they're not supported by the floor horizontally. It's just friction. That's the only thing that's supporting the floor horizontally. So that's how these legs are acting. This is our support condition. This is our support for this as a cantilever, and then this is our free end. And that's the main configuration of table you probably see. And the reason is because this is what most people do for dining tables. With a table, you want to be able to get, with a dining table, you want to be able to get your feet under it. You want to be able to get your chair under it. If we had a beam here, which is what I'm going to do in my next example, if we had a beam here, we wouldn't be able to get our feet under it, and it wouldn't act as a dining table. So this is the first kind of table that I want to talk about. And the second one is similar but different. So the second kind of table I want to talk about is what I would call the propped design. And by adding in a member at the bottom that connects all 4 feet of the legs together, we can transfer the load much more efficiently around the structure as a whole, and we can get away with much smaller members. So whereas the table before that I drew, I had these big chunky legs, because they're cantilevers, they're going to move and they're going to deflect, and I want them to be stiff, so they're going to be big and chunky. And the beam that it connects to has got to be big and chunky because it's got to transfer the same moment really at the end of the day without the same sort of deflection and flex. But it's also got to be big enough that we can get those two bolts in. It's no good if we pick a very small member, and then as we're putting that connection under force, those bolts just force themselves out through the wood. If those bolts have got to be a certain distance away from the edge of the piece of wood, and you need 2 of them, and then there's got to be a good distance between the 2 of them. So the limitations on the structure is much greater for the cantilever one. With this props design, we can just fix the legs into the tabletop and have them propped at the feet, and it won't have the same overall structural negative effect because these braces at the bottom of the feet, they transfer load around. Now, if you're an engineer and you're used to designing buildings, then you might look at this and think, no, there's no way. That's not going to do the job. Structurally speaking, these braces are not going to hold it all together. And the reason is because the difference between buildings and furniture, when we're talking about the table like this, is that when you put sidewards lateral load on a building, it's fixed to the ground, it can't move. So all of that load is transferred into the frame, and that frame needs to be able to absorb all of that load. Whereas when we're talking about a table, the tables aren't, generally speaking anyway, they aren't generally speaking fixed to the ground. So when we push it, the only force that we need to overcome is the friction on the feet. And the moment we overcome that friction on the feet, then there's no further force can be exerted on the frame because the frame just moves. So there is a fundamental slip mechanism in a table, which means that there's the amount of force that can be supported and transferred into the structural frame itself is based on the amount of friction on the feet of the feet. If you place this table on an ice rink so that there was no friction on the feet, then you could just push it and it wouldn't, and no force would be exerted onto the frame itself. So from an engineering perspective, that's where these pieces of furniture differ from structures, is that they're not fixed to the ground. Now, what I want to talk about with this is probably not the right, this is not the sketch that I've drawn out is probably not the right perspective to discuss the merits of both of these approaches. And to be fair, you know, this is a crude sketch. I've just done it freehand just to give you an idea of the sort of thing I'm talking about. What I want to try to do is give you some, let's look at some slightly different perspectives. When we deal with frames like this, we generally tend to look at them from a two-dimensional perspective. So if we would go back to a three-dimensional idea, we would see that, you know, that if we were looking down on the table, for example, we would see that as two orthogonal directions, and we would treat each of those orthogonal directions separately. So we would apply a force to one frame, and then we would apply the same force to the other frame, and then providing both of those frames independently can support the load in each of those directions, then the frame will be able to do the job. And so when we're generally looking at these frames, we're looking for the weak direction. And the weak direction is generally the longer span. You know, this is going to bend more. If we were looking at the other direction of the other perspective of the table, that's much shorter, and that as a frame will generally be much stiffer. So when we're looking for the worst case of what this frame is going to be doing, we look at the long frame directions, or at least that's how I'm going to look at it from these furniture perspectives anyway. It's a little bit different with buildings. So what happens when we apply a force here, a lateral force, is that this frame will generally kind of bend in a curved way like this. I wonder if I can get this right. And then this member will stay. So that's the cantilever. We are pushing here. We are getting a resisting force from the friction of the feet here and here. And that causes these legs to bend. And then once we overcome this frictional force, as I was just saying, the table just moves. So this frictional force is really all we're caring about. Not that we can really calculate it. But anyway, when we apply a force to this one, this fixes this leg. This tends to fix the leg in position. Not from a purely engineering perspective, but under smaller loads. You know, when we're talking about small loads, these things have a lot more strength than, you know, than can be demonstrated in an engineering world. You know, when we're dealing with big things, the small elements, how they fix together, it really matters. But we're dealing with small pieces of furniture like this, you know, that it just needs to be a single screw, and that will do a hell of a job. So what will generally happen with the new kind of deflected shape, if we put it that way, we kind of, oh, that's bad. It will kind of, let's do that again. It would bend one way and then the other. I know I've kind of drawn this kind of maximum deflection, this dimension that the frame is moving by, approximately the same. What you've got to appreciate is I'm exaggerating this for effect so that you can see what's actually happening, or at least you can understand what I'm trying to demonstrate anyway. So the deflected frame is different. The deflection is different. Because we've got this prop at the feet, we are able to achieve some kind of moment force here, which restricts the movement of the frame itself. And as a result of that, we can get away with a much simpler frame. In general terms, these are much more solid. As I said, the reason why you do a cantilever is because you want to have a table, you want to have a chair underneath, people want to get their feet underneath, you want to be able to eat on the top of it. If you don't have that same restriction, then you can get away with a much lesser structure, and it will be much stiffer and much stronger as a result. Now, if we look, what I wanted to do now is to look at the other directions, the short directions. So in the shorter direction, I mean, if we imagine that these are, say, a piece of 4x2, so they're 100 mil in 4 inches, 100 mil in this direction, and they're 50 mil in this direction, 2 inches, just for example. That would suggest that this is weaker in this direction, and it is. It is weaker in this direction, but it has inherent strength because it is shorter. This central beam has much more. It's not prone to deflecting and moving. So, in this direction, although we end up with a smaller member size, effectively, doesn't really matter too much because the direction is shorter. Now, if we were talking just general terms, the rule that I generally come up with is that the shape and size of the legs of your table should match the shape and size of the table itself. So, if for example we had a long thin table, then we would want to use long thin wood legs. If we had a square table, then we would want to use square legs, because that matches up the strength requirements that are required based on the dimensions of the table itself. That's my key rule when it comes to these sorts of cantilever tables, is to try and match up the size of the legs. Now, if you're doing a very big square table, then you won't want these to be big 4 or 6 inch pieces of wood square. Whereas if you're doing a long thin one, you can get away with much thinner legs if you did it this way. That's my general rule. Now, in the short direction for this one, we essentially get the same effect that we've got up here. So the dimensions of the legs aren't really all that much important. They're just going to deflect a little. I don't really know how much to explain, because this is just a much better design. And if you've got the opportunity to do it, then that's what I would recommend you doing. You know, for example, the workbenches that I've got down in my workshop, they're this, because I don't need to get my feet under it. And you know, these are just bars. If we go back, let's have a look at this sketch. These are just bars. I can store stuff in here, you know, quite easily, quite happily. I don't need to be able to put my feet under it. And if I've got a stool down there, if I had a stool here and I'm sit underneath it, I can just dangle my legs in here. It's for a solid design. I reckon that I've actually thought about. I've thought about dropping them off my workshop roof to see if they stick together, because they're really solid. They don't, and I am just about to replace them, so I could do some funky test with them and see. You know, that might not be a bad video to make. Anyway, so that's what I wanted to talk about with the cantilever kind and the propped kind. And these are, generally speaking, squares or rectangular tables. So let's take this a step further. Let's take this into the fanciful, and let's have a think about what a non-square, non-four-sided shaped table might look like. I'm not going to draw this in three-dimensional isometric because it's just a nightmare. So let's just have a look at a triangle. So whereas with a square, we deal with it in two directions because the two frames are doing the same thing. So we only have to design one of them, and we'll by extension we'll know the other one. So we've got four frames essentially, but two of them are identical. So we only need to design two of those frames. With a triangle, we would be thinking about it. Well, we've got to think about it in 3 dimensions. So we've got to think about this frame. We'd have to think about this frame. Oh, that's a really bad line. And we have to think about this frame. So we would have to deal with. We would have to, along each of these 3 principal directions, we would have to have a comparable frame to go in it. And each of those, depending on the dimensions of the triangle, might be differently shaped, differently, you know, dimensioned. I mean, I don't know what to say about this. You really want right angles, because your legs are going to be square, you know, so you'd have to plane it down, chamfer it off or something. I don't have a tool that would do that in my workshop, so yeah, I mean, triangle tables, are you really going to do triangles? I've never made one. Anyway, let's go to the next level. If we're talking about 3-sided, I'm not going to do 5-sided. Let's have a look at 6-sided shapes. So, for a 6-sided shape, we're probably dealing with 3 dimensions, the 3 dimensions that we're dealing with, the same with the triangle. But because we have reflection, we're only dealing. We have 6 frames, but we only have to deal with 3 of them, just like a triangle. I'm going around in circles. So from my perspective, there's probably two different ways to look at this. You can deal with it as the outside frames. Let's just deal with that for a moment. So we would have to put a frame along each of these lines, and that would work probably quite well. Probably not ideal, you know, because when you push, if you imagine I'm pushing on here, then what this is going to want to do is this is going to want to move inwards, and that will push this outwards. I'm exaggerating, and I'm not exaggerating all the wrong parts, but you get the idea. Because there's no central brace in here, that force is having to shift its way around the structure. Obviously we have a tabletop on here, and that's going to do a really, really good job spreading the load around these beams if we did it in this manner. As long as it's all fixed down, properly glued and everything, then it will act as one. But as a structure, it is inherently a little bit weak because of it's not got that strength in here. So when I apply, if I apply the force here, it will do exactly the same thing. It just do me in a different direction. So, you know, I know we're dealing with the theoretical here, and I'm pushing the boundaries of what's really sensible for a table. But you know, that's really where we're dealing with engineering. Engineering is about taking a principle, a solid principle, and then seeing how far it takes you. You know, what changes when we change these fundamental things. So from my perspective, from a carpenter, you know, what would if someone came up to me and said, "Oh, I really, really want a hexagonal table," then how would I think about it? It's an interesting quandary. Obviously, I've had time to think about it before I've sat down here, but you know, it was an interesting thought experiment. So the way I would probably deal with it is I would deal with it in the principal directions like so. So instead of having a frame from here to here and a frame from here to here, etc., I would have a frame that linked from here to here and then from here to here. And that way, when I push on here, that force has got somewhere to go along this member. I know we've got the tabletop, and I've said that already, and that will do really, really well, but I also want you to appreciate the way that, you know, if this wasn't a table, if this was a hexagonal structure, how we might approach it. I mean, to be honest, if this was a building, let's do that thought experiment. That's an interesting thought experiment. So if this were a hexagonal building, how would you design it? Probably, actually, you know, think about it, it'll probably depend on the roof. You know, what is the roof doing? If the roof is going up and then down, then I would probably deal with it as separate frames, like so. These would be my frames. And then so that would work quite well with a roof that went like this. If we had a central point and everything kind of led up to that roof, then you probably have to put a truss in or something to deal with it, to get that point to support itself. You probably, if we were looking along this line, we probably need like a truss or something. And then one of these lines would be a truss, and then these other two lines would span onto it. That's probably what you would do, something like that. If I was designing it, you could probably make a really good case, you know, a really good design of where if this was a complete, like a cone sort of shape. I don't really know the specific term. There's probably a specific mathematical term for what this geometry is. I don't know what it is, but you could probably make a case that if you had this member acting as a tie, then you wouldn't need this truss. And it would, you know, if you push down on here, then it would try and push the structure outwards, and this would act as like a ring beam trying to confine it all in. There's a few different ways you could go with it, I suppose, thinking about it now. But yeah, it's probably that one. Oh, that was the that one, or this one, where I think of it as frames like this. That's probably where I'd go with it. But to go back to tables, that's generally how I think of them. You know, the cantilever kind and the propped kind, they are very, very different, and they make different structural demands on the type of thing that you're on the furniture that you're making. But that's really all I've got to say. I think I've covered all the things I wanted to talk about. I hope it's been interesting. Till next time.